for Chem 200. We're adjusting for our remote learning, so we're going online. We're going to be starting with Chapter 8. If you haven't looked on Canvas at our adjusted schedule, please do so. These videos will be broken up into smaller chunks, so we're not going to do all of Chapter 8 in this one go. As you can see here, this video will consist of the information in sections 1 through 3 of Chapter 8. So really where we're going to start off with this chapter, let me mention really quick, this will be much more meaningful to you if you either can print out a copy of the slides that are posted to Canvas, or if you can't do that, to at least have them open with the video so that you can watch me as I'm going through it and take notes. The other thing that will be really useful for you, especially for this chapter, will be some scratch paper to do practice on, as well as a periodic table. All right, so really section 1 of this chapter deals with the concept of a chemical bond. So we kind of know what those are, right? The technical definition, as our book says, is a force that holds groups of atoms together and make them a functional unit. This is a really fancy way of saying the force that holds atoms making molecules together, right? So we have an idea in our head of what a bond is, but we're really going to start diving into the different types of bonds, different type of energy associated with bonds, and really how those bonds are made. So one of the things that we've talked about before is bond energy. We talked about this in chapter 6 a lot in our thermochem. Remember where I would hold my arms together and then burst them apart and say that energy is being released when we break a bond apart, or that sometimes energy is required when we form a bond. So what we're going to be dealing with in this chapter is talking about why. Why is energy, where did that energy come from in that bond when it broke in an exothermic reaction that would cause it to release energy? Where did that energy come from? The first type of bonds that we're going to talk about are ionic bonds. And you should be familiar with ionic bonds. We've been talking about them all semester as well as in 152. And we know that they result from the attraction between a cation, a positive charge, and an anion, a negative charge, right? And those positive and negative charges are attracted to each other, and we call that attraction, where they stick together, electrostatic attraction. We know, right, the like recipe for an ionic compound would be a metal and a nonmetal. The metals make our cations, the nonmetals make our anions. So the classic example we always have is table salt, NaCl, where Na is our metal, our cation, and Cl is our anion. We know that the sodium will give up an electron and become a cation, and the chlorine will accept that electron and become an anion. So the first thing we're going to talk about is Coulomb's law. This is just an equation we have basically to interpret the amount of energy that's in that ionic bond. And there's a constant here, and then Q1 and Q2 are going to be the numerical charges. So if Q1 represented my sodium, this would be a +1 charge, so +1, and if Q2 was my chlorine, this would be a -1. And it would be divided by the distance between the two centers of our ions, right? The sodium ion and the chloride anion. There are 3 different ways. If we had, for instance, a chunk of table salt, if we had a chunk of sodium chloride, what we would have would be the repulsive forces, right? Because think about it, it's a lattice, right? It's a cube where we have NAs and CLs all held together. So there are repulsive forces between the sodium atoms, right? An Na plus and an Na plus that are near each other, those have a repulsive force. A chlorine minus and a chlorine minus that are near each other are also going to have a repulsive force. But there's also an attractive force of the Na plus and the Cl minus. So the sum of those 3 different energies would be the overall sum of the positive, or excuse me, of the energy associated with the NaCl. I do have a link in Canvas to a greater definition of Coulomb's law if you need it. So when we're talking about bonds, right, when bonds are being made, if we have 2 identical atoms, the example we're going to give is with hydrogen atoms. So we know hydrogen is diatomic. That means, you know, an individual hydrogen atom doesn't exist happily in nature by itself. It wants another one. So a bond will form if the energy of the 2 atoms together is lower than the 1 atom by itself. Remember, nature's lazy, right? It'll form a bond if that makes the overall system, right, the molecular compound have lower energy than it did by itself. So that's what we're seeing in this diagram here. Here is hydrogen. Hydrogen, we have over here like the energy as well as the distance between the two atoms. So these are hydrogens that are coming closer and closer together, and the closer and closer they get till they reach this ideal bond length, right? This is the bond length of a hydrogen, or excuse me, an H2 molecule. This is the lowest energy possible. So when we reach the lowest energy, that would be where the bond length is, as we normally know it. Now, as those hydrogen atoms get ripped apart, further and further away from each other, there comes a point at which the energy starts to increase because hydrogen, as we know, don't like to be alone. So we know that once they've gotten farther enough away from each other that they no longer can share their electrons, they're at a higher energy state than they were when they were bound together. So what does this really mean? Energy terms are involved. When we say a net potential energy, we're talking about the attractive and repulsive forces of whatever molecule we're looking at. In this case, those two hydrogens. The kinetic energy is as those hydrogens are moving into position or moving away from each other. 0 point would be where those two hydrogens were further away from each other, where we kind of saw that line flatten out. There's no increase in energy the further away they get, right? There comes a point at which that's the high energy point. At very short distances, right, the energy rises steeply because of repulsive forces, right? So if we have two hydrogen atoms and they're in a nice happy bond and, you know, they're where they're supposed to be, but then we force them to get closer to each other, we're going to have repulsion forces. But the bond length is that kind of sweet spot, that lowest energy conformation. So we talked about ionic bonding, and we know that that's an electrostatic attraction between a positive charge and a negative charge. And we know that covalent bonding, right, is the sharing, covalent, the sharing of valence shell electrons. And we know this could happen between two of the same kind of atoms or two different atoms. So in an identical atoms, right, so H and H, Cl and Cl, C and C, right? The bonding results from mutual attraction of the nuclei and the shared electrons. So an example of a chlorine atom covalently bound to another chlorine atom, each of those atoms only needs one more electron to complete their octet. So if they share two of their electrons, they each complete it. So the bonding results from that mutual attraction of the nuclei to those shared electrons. We also are going to start talking about this concept of a polar covalent bond. So up until now, we've been talking about covalent bonds and saying, oh, they share the electrons, everyone's so nice and happy. We're going to start learning that not every bond that is covalent shares the electrons equally. So what ends up happening is, oftentimes there will be an atom in the bond of a covalent bond that holds the electrons more tightly towards it than the other atom, which means we would have electron density on one end of our bond and an electron deficiency on the other end of the bond. We're going to look at an example of this with hydrogen fluoride, HF. So what we're showing here in this diagram is just what happens in an electric field. When we have HF, H, right, and F, if you look on your periodic table, hydrogen is all the way on the left-hand side, fluorine is pretty much all the way to the right. What we'll find out is that the hydrogen will have a slightly positive charge, and we'll talk about what that means, and the fluorine will have a slightly negative charge to it. Now please make the distinction here. This is not an ionic compound. HF is a covalent compound. This is not a cation, and this is not an anion. That's why it has this little S here, okay? It's a Greek symbol, but for you to understand it better, it means slightly. Okay, this is not a real anion and it's not a real cation. It just means that there's more density of the electrons sitting on one end than on the other end of the bond. So when there's no electric field, right, the atoms will just kind of hang out willy-nilly. But when we start running an electric field over it, we'll see that they will align themselves in a way, right, that the positive charges would be attracted to the negative side of the plate, and the negative charges would be attracted to the positive side of the plate. That's all this is trying to show. So what type of bond is formed when electrons are unequally shared by the nuclei? Take a minute, pause, figure it out. polar covalent bonds. So remember, we have ionic bonds, covalent bonds, and we're going to have polar covalent bonds. There's no such thing really as a polar ionic bond. It's understood that an ionic bond is inherently polar because there's a cation and an anion present. So for us to get a better understanding of this polar covalent bond and how we can figure out if something is a polar covalent bond, we need to talk about the concept of electronegativity. And really, it's the ability of an atom in a molecule to attract shared electrons to itself. So when we say an atom is very electronegative, that means it likes electrons. It's going to hold and hoard and surround itself with the electrons in that bond. So the electrons will hang out closer to that atom, the shared electrons, than it would to the less electronegative atom. One way this can be determined is with Pauling's model. I'm not going to go into this in too much detail. I won't be asking you to calculate bond energies in this way. I'll show you in a few slides one of the kind of general trends that you will need to know. Basically, one of the big things I want to talk about here, though, is this right here. When we have identical electronegativities. So for example, if I have a chlorine and a chlorine, even if we'll learn that chlorine is a very electronegative atom, that means that it really likes to hold on and pull electrons. If it's pulling electrons against another chlorine, then both of those chlorines are pulling equally. So there would be no difference in the electronegativities. So overall, those electrons are stuck in the center of the bond. When we're talking about polar covalent bonds and determining if we have a polar covalent bond, you kind of want to think of it like tug of war, right? So on each end of a tug of war, if you have the rope and you have the little flag in the center, the little flag in the center are the electrons that are being shared in that covalent bond. And we have two atoms or two people pulling on that rope. If we have a very electronegative atom, that would be like a big, strong, like football player. And if we have a very weak electronegativity for an atom, that would be like a kindergartner. Okay, so you can kind of imagine in your head who would win in that tug of war, right? Which way are the electrons going to go? So when we have greater electronegativity, right, when we have a linebacker for a football team pulling against a kindergartner, we know the electrons, even though we've been drawing, right, the electrons where it's like dot, dot here in the center, they're actually hanging out down here on this side of the bond. They're still being shared. Again, I cannot iterate this enough. This is not an anion. This is not a cation. This is still a covalent bond. It just so happens that both electrons are hanging out on this end. So there's more negativeness kind of concentrated on this side of the bond. And because all the electrons are hanging out down here, this side of the bond is slightly positive. So slightly positive, slightly negative. Not anion, not cation. So the greater the difference we have in these electronegativities, the greater what we say the ionic component of the bond is. Now, it's really, really important. When we say ionic component, we're still talking about covalent bonds. They're still sharing these electrons. It's not an ionic compound. It's just got ionic-like characteristics to it. Okay? It has this slightly positive, slightly negative thing going on. It's not a true ionic bond, okay? So what we're learning is that covalent bonds kind of live on this spectrum. They live on the spectrum of perfectly being shared, where there's no polarity, and each atom is equally getting kind of the feel of all the electrons, to having a very unequal sharing, right? And it's the spectrum of everything in between. So, instead of going through Pauling's model, what we're going to be using is this general trend here. So on your periodic table, I would really encourage you to actually write these two arrows and start learning and memorizing this general trend. Now, we're going to start with the decreasing electronegativity going down. So over here, this entire image is helping us understand electronegativities. So on the right-hand side, the top right-hand side of the periodic table, as we go from top to bottom, and that's the same for over here, top to bottom, we will be more electronegative at the top, and we will be less electronegative at the bottom. More electronegative, less electronegative. One more time. More electronegative, less electronegative. So how is this happening? Why is this happening? We know that electronegativity is the ability of an atom to pull closely to it the electrons it's sharing. So let's think about lithium for a second. What is another trend we know that occurs as we go from top to bottom? When we go from top to bottom, we know that this atom, the radius is small, and that this atom, the radius is large. Right? Think about your size of atoms. So we're saying that smaller atoms have greater electronegativity than larger atoms. And this should make sense. Think about it for a second, right? If we have an atom, right, a circular atom, what is in the center? The nucleus. That's where the protons are. What's around the outside? The electrons. Those are negatively charged. So if we have a tiny little atom, that means the positive center and the negative outside are fairly close to each other. So they're going to have strong interactions with each other. And if we have an extra electron being shared, then if it's a smaller atom, then that shared electron is going to have a better chance of interacting with the close nucleus because it's so small. But as our atom gets bigger, right? The atom gets bigger because we go down n equals 2, 3, 4, right? So on and so forth. As we go down, we get more and more layers to our atom, right? Think of like an onion, right? The outer shell is the valence shell electrons. That's where we're going to have the covalent bond occur. So as the atom gets bigger, the center of the atom and the valence shell electrons get further and further away from each other. So the pull of a valence shell electron and outer shell electron is much weaker from the nucleus in a bigger atom than it is in a smaller atom. And that's why we see this trend. I think this would be a really good place for you to pause and come up with your own sentence on how you would explain this trend. This is something you will need to be able to explain in words. Why do we see the trend that as we go from the top of the periodic table to the bottom of the periodic table, do we see a decrease in electronegativity? So I would encourage you to take a pause here, maybe review, rewind a little bit, and come up with a good sentence for yourself, or 2 or 3 sentences to help describe that. Now we're going to talk about this trend we see going across the periodic table. As we go from left to right, we increase in electronegativity. That means as we go from left to right, we are getting more electronegative, which means the most electronegative atom in the entire periodic table is fluorine. Okay? It's at the top, which means it's small, and it's also all the way across at the right, which means it's very, very electronegative. So if you're looking at our chart the way it's done, it's also the highest step, meaning its value for electronegativity is a 4. It's the highest number. Now, as we go across the periodic table, what is the trend we know in atomic radii? As we go across the periodic table, right, in a row, in a period, that's right, the radius gets the radius gets smaller. So when we compare lithium to fluorine, fluorine is smaller than lithium. So again, that same trend of the smaller atom is going to be able to hold on to those electrons more tightly. So top row, right-hand side, fluorine, very, very, very tiny atom, allowing it to be very, very electronegative. Again, you should be able to describe this trend and explain why, as we go across the periodic table, we see an increase in electronegativity as well. So, we know 3 different types of bonds. We have an ionic bond, a nonpolar covalent bond, and a polar covalent bond. Those are the 3 types of bonds: ionic, covalent, polar covalent. Oftentimes you'll see covalent also written as nonpolar covalent, just so that you know. So the way we can describe this is when we have a difference in electronegativities of 0 or very, very small differences, it would be a covalent bond, a pure covalent bond, nonpolar. No one's hogging the electrons. So let's look at some examples. A hydrogen has electronegativity of 2.1. A carbon has an electronegativity of 2.5. These are small enough in electronegativity differences, that we consider a CH bond nonpolar. When we have a fairly decent amount of difference between our electronegativities, we'll end up with a polar covalent bond. They're still sharing those electrons, they're just not sharing them well. So for example, a carbon and an oxygen, they have a difference of 1, right? A 2.5 and a 3.5. Again, you won't need to memorize any of these electronegativity values. We're going to go by this general trend, and I'll have some general overall recommendations for you to memorize. But this is an intermediate difference. So if we had a bond between a carbon and an oxygen, the electrons that are shared between that carbon and oxygen would be closer to the oxygen side of the bond. And then lastly, when the electronegativity difference gets so big, it's no longer sharing them. It's actually an ionic bond. It would be something, for example, a sodium and a chlorine. We're almost 2 whole electronegativity values away from each other. This is a pretty extreme electronegativity difference. And we know this is an ionic bond because we know the sodium is going to give up the electron and the chlorine is going to take it. So that's where we get this kind of range of covalent character and ionic character. A nonpolar covalent bond is a pure covalent bond. The electrons are shared and they're shared equally. A polar covalent bond is still a covalent bond. They're still sharing the electrons, but it's getting more ionic character because it's now not sharing them equally, right? Not sharing those electrons it's sharing equally. It's that football player and the kindergartner playing tug of war. And then an ionic bond, no sharing at all is occurring. It's a give and take, which would give it full ionic character. So, order the following bonds in according to polarity. So what I'd like you to do here is take these bonds and order them in such a way that we go from least polar to most polar. One of the good things that you can do, like we said, you do not need to memorize these values. Just memorize the general trends that we see. For the most part, when we're dealing with covalent compounds, we're kind of just dealing with these guys right here, right? So as long as you know your periodic trend, you can figure out which of those bonds will be the most polar and the least polar. So I'm going to pause here. You should pause the video, take a moment, and organize these. So when we look at polar bonds, as they increase in electronegativity, we're going to have these differences. In the 5 examples that we had here of 5 different types of bonds, they all share a hydrogen. So that's what we're comparing here, right? A hydrogen to different elements. Now, I made a note here. It does not matter, regardless of the identity. It doesn't matter if it's a carbon and a carbon, a hydrogen and a hydrogen, a fluorine and a fluorine. 2 of the same atoms bound together will never be polar covalent. That's really important. I think you should write that down. 2 atoms that are bound covalently, that are identical, will never be polar covalent bonds. They will always be nonpolar. After that, we're going to start looking at the general trend as we go across the periodic table, right? Sulfur, chlorine, oxygen, fluorine. This would be the most polar bond because we have a greatest difference between our electronegativities. So here is just kind of showing the differences on a scale to kind of help with it. Over on this side, 0 to 0.4-ish, we consider this non-polar covalent. Non-polar covalent means, for all intent purposes, the 2 atoms in the bond are sharing those electrons equally. So there's no slightly positive side, there's no slightly negative side. As we get a greater and greater difference in our electronegativities, we're starting to go towards a polar covalent bond. And then if we went to the extreme end, we would actually be over here. This would be an ionic bond over here. So I want you to, without using that, figure with the values for the electronegativities, kind of come up and put these atoms in each of these groups in order of increasing electronegativity. So again, just look at your periodic table. Remember our general trends. Pause the video here and try and do this. So I'm just going to go through this first one with you really quick. You can look at the other ones, but they all follow the trends. We know that carbon is more to the left than nitrogen, then oxygen to the right. And we know that we increase in electronegativity as we go from left to right. You can do the same thing going top to bottom, so on and so forth. All right, so here is our first quote-unquote door question. Since I can't have you go to my office, within our slides there will be door questions. These are just like we treated door questions in lecture, so when we were on campus. So I'm just going to leave this up here for you guys to munch on and think about, and might show up on a quiz or a test at some point. I would like you to think about this. Which of the following elements forms the most ionic bond with chlorine? So when we're talking about the most ionic bond, we're talking about, right, going on this end, the most ionic character, okay? The most ionic character, that biggest difference in electronegativities. So you're going to have to look at your periodic table to figure out what's going to give you the greatest difference here. And in this case, to get the most ionic bond, we're going to want potassium, right? These are going to have the greatest differences in electronegativities. And when we look at the periodic table compared to these other ones here, we know that chlorine and bromine doesn't make any sense. Those are both halogens, right? And so they would have to be a covalent bond. And we know that they're relatively close to each other in their family, so they're not going to have a huge difference. Krypton, that's a noble gas, so we're really not going to have ionic bonding going on with that one. Phosphorus, again, this would be a covalent bond, and then aluminum and potassium. These are both metals, so these will make ionic bonds. And then we want to talk about what's going to be the most extreme one. So we're going to talk about who's going to have a more larger difference in our electronegativities. And so in this case, it would be the potassium. Now, like I have in my definition here, we talk about the most ionic bond results from the largest dipole moment. And up until now, we've just been talking about this in terms of our differences in electronegativities. So now we're going to talk about what do we really mean when we say a dipole moment. So a dipole moment is when we look at a bond, right? Molecules are going to have these different centers to them, a slightly positive center and a slightly negative center. Dipole, di meaning two poles, a slightly positive pole and a slightly negative pole. That's literally what it means. There are a couple different ways we can draw these dipole moments. The first way is with an arrow. And here we pretend this is just an HF bond. Here's the H atom, and here's the F atom, and here's them sharing their electrons, right? Now we know fluorine is very electronegative, and hydrogen really isn't. So we know that the electrons are really hanging out on this end of the bond, which means this side of the bond would be slightly negative, and this side of the bond would be slightly positive. So one way we can represent that is to draw an arrow through the bond. The head of the arrow points towards the electrons, and the tail of the arrow, if you can see there is a positive sign in the tail. This represents that this side of the bond is slightly positive, and this side of the bond is slightly negative. Another way we can write this is with these two symbols down here. Again, this is a Greek symbol, but for what we really care about, this means slightly positive, and this means slightly negative, okay? So we could write them out like that as well. As we move on, we're going to go from just a bond to a whole molecule. So sometimes we could have really complex molecules where maybe it'll be easier to draw out just, highlighting slightly positive, slightly negative instead of having a whole bunch of arrows. So both of these ways are very useful in understanding our dipole moments. Another way you'll see it in your textbook and online and in your homework are these electrostatic potential diagrams. These aren't things you will draw. They're usually generated by a computer, but I just kind of want to show you what they look like so you understand what understand what it is when you see one. Red will typically indicate a very electron-rich area, so this would be the slightly negative side. Blue will indicate an electron-poor region, so this would be slightly positive, this would be slightly negative. So for example, here's our HF again. We knew we had the arrow where the head was pointing this way, and the positive tail was over here, or we had the slightly positive on this side, the slightly negative on this side. This is just another mapping way to kind of show it. A lot of electron density over here, very little electron density over here. So hydrogens with different halogens. Just showing you the general trend we see here. Now HF is going to be really extreme. We know that because hydrogen is very small and not very electronegative, and we're with fluorine, the most small and electronegative atom that we have. So that has a huge, huge, huge dipole moment, very big. And then HCl, HBr, HI. Now, as we go down the periodic table, right? Fluorine, chlorine, bromine, iodine. Small, slightly bigger, right? The biggest of those halogens. Do we see how the dipole moment decreases? That's because when we go down the periodic table, electronegativity decreases as well. So when we look at HI, we don't really have a polar compound anymore. We don't have a polar covalent bond anymore. We just have a covalent bond. So we typically say that a covalent bond will occur between a hydrogen and a halogen, but just remember the halogen of HI isn't really going to produce a polar bond. Here's an example with the water molecule. This is what I was saying, as we get bigger, more complex molecules, it starts getting a little harder to kind of draw everything out. These are in the different ways we represent that polarity, right? Those different dipole moments. So in a water molecule, we actually draw a water molecule like this. Later this chapter, you'll learn how and why we draw a water in this kind of V bent shape that we have going on here. But right, H2O. We know that in an HO bond, the hydrogen would be slightly positive and the oxygen would be slightly negative because the oxygen is more electronegative than the hydrogen. So the electrons are hanging out on this side of the bond. And they're hanging out on this side of the bond in this hydrogen as well. Does that make sense? Each of these is its own bond. So slightly positive, and this would be overall slightly negative. Now, when we draw our arrow, we only see one arrow here because, again, think of this almost like a boomerang, okay? It's flat like a boomerang, but it's also bent. Now, let's say I took a knife and I cut straight down here. If I took a knife and cut right here, these would be my slightly positives on one side and my slightly negative on another side. So when we draw our arrow, our polarity arrow, we have just a general arrow for the whole molecule. You could have a slightly positive, negative arrow going this way and the head of the other arrow pointing this way, but if we combine those two arrows, it would be like taking a knife and cutting straight down here. These would be my slightly positive side, whoops, and this would be my slightly negative side. That's what's being represented in this drawing here, in our electrostatic diagram. Again, you will not be drawing these. I just want you to be able to be comfortable with drawing both of these. You will have to draw polarity arrows, and you will have to draw the slightly positive, slightly negatives. So, this is going to be a weird concept that we're going to talk about, and the further we go in this chapter, we're going to get into more detail with it, but I want to start kind of bringing this to your attention. Some molecules have polar bonds, but do not have a dipole moment for the overall molecule. All right, so what does that mean? Let's go back to here for a second. Would you agree that HO is a polar bond? Yes, right? We know that H and O don't share the electrons equally. So this is a polar bond, and this is a polar bond. There are two polar bonds in this molecule. And when we look at the overall molecule, there's a dipole moment for the molecule, right? We said we could cut this molecule in half. This side is my slightly positive. This side is my slightly negative. There's my dipole. Now, not every molecule will have this occur. We can have a molecule where it has polar bonds, but is not polar overall as a molecule. And for right now, you don't need to predict these. You just have to understand the concept. And we're going to use CO2 as an example for this. So CO2. This is the Lewis structure of CO2. Now, CO2 is a double bond between the carbon and oxygen here, and a double bond between the carbon and oxygen here. And that's fine. Let's look at just this CO bond for a second. We know that oxygen is more electronegative than carbon, which means the electrons are hanging out on this side of this bond, which means this oxygen would be slightly negative and this carbon would be slightly positive. The same thing is happening on this side of the bond. So if we were to draw out our polarity arrows, they would look something like this, right? Where the the slightly positive tails are both on the carbon, and each of the heads of the arrows are pointing towards the oxygens. Now, unlike our water, which was shaped like a boomerang, right? Our CO2 is a flat line. It's symmetrical. So what ends up happening in CO2 is we have a molecule that contains polar bonds, but overall, this whole molecule is not polar. There's no way I can cut this molecule where I get my slightly positives on one side and my slightly negatives on the other. It doesn't work. I can't cut this in any way where I get one concentration of the pluses and one concentration of the minuses. So this overall molecule is non-polar, even though it contains polar bonds. Now, again, just like I had you do with your electronegativities on that periodic table, I want you to pause here and write a sentence or two to explain to yourself. I want you to be able to explain, how is it possible that a molecule can contain polar covalent bonds but not be overall polar? Okay, this is a very important concept. So if you need to pause here or rewind, I would encourage you to do so. We will get more into this later on this chapter, but I just want to give you some examples of where we can have polar bonds, but overall the molecule would not be polar. So CO2 is our first example. These are little model kits. In lab this week you are doing the model lab, and I will also post into our lecture extra resources portion some free online simulators you can use at home to play with, like an online model kit to look at. But here's CO2. We already did CO2. We went through the whole explanation. Here's an example of SO3. Sulfur in the center, oxygens on the outsides. This is a polar bond. There are 3 polar bonds. The sulfur is slightly positive in all these cases, and the oxygens would be the slightly negatives. Now, the problem here is this is flat. So instead of our boomerang like we had with water, just add another kind of little arm coming off on the side. So it's like a fidget spinner. It's flat, but equally separated out. So this would be like a really weird game of tug of war where there's a really, really strong guy in the center and 3 slightly less strong guys all pulling in separate directions around him, right? No one's going to win because these on the outside are all equally pulling on the center. So we don't have a side where we have a slightly positive portion to the molecule and a slightly negative portion to the molecule. There's no way for me to cut this molecule up where I would get that. And lastly, we have what we call tetrahedral. And again here we're showing a carbon and 4 chlorines around it. So we know carbon is going to be slightly positive and each of these chlorines would be a slightly negative. Now, it's hard to see in this diagram right here. Maybe you can see it a little better in the picture. But these are all evenly spaced away from each other. Just like in this one, they're all evenly spaced away from each other. This is symmetrical. All 3 of these are symmetrical. So when we have a polar bond in a molecule, but the overall molecule is symmetrical, the overall molecule will not be polar. So for each of the following molecules, right, these guys right here, I want you to go through and kind of figure out the direction of the bond polarities and then indicate which ones have a dipole moment. So when we say dipole moment, we're talking about is the overall molecule polar. So here's HCl. HCl, we know that the H would be slightly positive, Cl is slightly negative. We could also draw it with our polarity arrow. We could cut this down the center, right? This is not symmetrical, so I could cut it down the center and have a side that's slightly positive and slightly negative. So this molecule is polar. It has a dipole moment. Cl2. Now remember, Cl2, that means chlorine here and chlorine here. Chlorine is very electronegative, but this would be like the football player pulling tug of war with another football player. They're equally matched for each other, so there's no slightly positive, slightly negative. So there's no polar bond, and there's no dipole moment. There's no overall polarity to the molecule. We already talked about SO3, but I'll show it here again. Slightly positive in the center, slightly negative, slightly negative, slightly negative. So we have 3 polar bonds. But this is our fidget spinner, right? This is flat and equally spaced apart. So that's like 3 people all playing tug of war with each other, equally pulling. So overall, there's no dipole moment. This molecule is not polar. Again, here's kind of the overall drawing of our SO3 with our plus in the center and our slightly positive in the center and our slightly negatives around it. And lastly, CH4. This is an example just like the carbon tetrachloride we had. Same shape, but now we have carbon and hydrogen. This is a really important one I want to make note of. This is something you should be writing down in your notes. Carbon-hydrogen bonds. For the purposes of our class, carbon-hydrogen bonds will never be polar. I don't agree with how your textbook has slightly positive, slightly negative here. These are very minimal. They're so small that we don't really consider the difference in these electronegativities to be to be polar. So 0.25 and 0.21, we're only off by 0.04. So this is not considered a polar bond. Okay, so for our class, when we see a CH bond, this will be nonpolar. So overall, if we have no polar bonds in the molecule cannot have a dipole moment. The molecule cannot be polar. All right, and then lastly we have H2S. This is an example of H2S. It looks very similar to H2O, right? If we put an oxygen here, we'd be having the same thing again. Remember, this is our boomerang. So each of the hydrogens is positive. The sulfur is negative. I can cut a line across and separate my slightly negative from my slightly positives. So this has polar bonds and has a polar and is a polar molecule with a dipole moment. So, which of the following is the most polar bond without being considered ionic? So when we go through this, you may be looking and go, MgO. Oh, that's the biggest differences in electronegativities. But we know that the question is asking us without being considered ionic. So it still needs to be a covalent bond. We know that a metal and a nonmetal make a ionic bond. So this guy's out. The other one that should be obviously out really quickly is OO. We know whenever we have 2 of the same atoms, this will also be nonpolar. So B and D are not good options. So we're comparing CO, NO, and OF. In all these cases, they all have O's. So which one of these is going to have the greatest difference in electronegativity? CO. So think about where the C, the N, and the F are on the periodic table. We know fluorine's the most electronegative. We know that nitrogen and oxygen are nitrogen and carbon are very, very close to each other. So the differences between the C and the O and the N and the O aren't very big. But the difference between O and F would be much more, would be much closer as well. So our best shot here would be the difference between the carbon and the oxygen. Let's look at it the other way. Which of the following bonds is the least polar, yet still considered polar covalent? All right, so we know we're again talking about polar covalent, so we can't have the ionic bond. The other thing is we're talking about least polar, but is still polar covalent. OO is going to be a non-polar bond, so that one is out as well. So which is the best option here? There's two. Now, on a test or quiz, I wouldn't ask you this because these are so close to each other, it'd be really hard to determine them without doing the math. But in both cases, what we're talking about here is the idea that N and O are very close to each other, and O and F are very close to each other. So even though they're polar, their values are significantly smaller. Can you arrange the following bonds in terms of decreasing polarity? So I'm going to let you pause here a minute. I would encourage you to pause the video, go through and try and solve this. As you can see in all these scenarios, chlorine is our shared common atom, so use that to help you in your determination. So I would encourage you to pause and determine which one of the groupings is in correct order of decreasing polarity. A, S, P, and N. We're going from most polar to intermediate polar to least polar. And then lastly, which case is the bond polarity incorrect? So I'm asking you, when you look at these, which one of these incorrectly is drawn? In this case, aside from the fact that Mg, this would not be slightly positive, this would be a cation and another cation, which doesn't make any sense for that one. But what we see here is chlorine with a positive charge and the iodine with a negative charge. This is the end of our first video, sections 1 through 3 of Chapter 8. I would encourage you to start working on your Chapter 8 homework, as well as looking at the resources that are provided in our extra help section on Canvas.